Yes, sir.
Okay, so we'll start now. What I want to tell you today is a little bit more about. So I showed you the previous class that when the periodicity, the Fourier series, Fourier transform. K integral minus f of x e to the power I dx. Whether you use ikx or minus x, only thing is that doing the reverse transformation of the exponent when you are trying the f of x. So, for example, capital dk. Okay. So the integral of x will be a function of k, and the integral of k will be. Okay. Now, having said this, let us see what happens when multiply the function by. I'll make another function. Differentiation. So let me call it f equal to e to the f of x. So now I want to find out what the Fourier transform of f tilde is. Tilde of, or f tilde of k is equal to 1 integral minus infinity f tilde of x e to the I k x dk dx rather. Okay. So now when you do this, let me substitute for f tilde. Integral minus infinity to infinity f of x e to the I k x e to the alpha x dx. Or I can actually write it, usual way. It is integral minus infinity f of x e to the I k x dx minus I of x. Okay, this because I times minus I alpha is plus alpha, so it is going to give me the same function as before. So what is this equal to? This is equal to f of k minus I alpha. So what we have is if is equal to Fourier is equal to f of k, then Fourier transform of f of x e to the power alpha equal to f of k minus. That means I actually shifted origin of k to I alpha. So this is called the shift. Okay. Now let me give you a few more. If function f of is an even, That means f of x is equal to f of okay. Then f of k is equal. How do you show this? Let me take f of k is equal to 1 integral minus infinity f of x e to the ikx dx. Okay. Now, because f of x is equal, I can write it like 1 upon root integral 0 to infinity f of x e to the ik dx plus integral minus infinity to 0 f of x e to the minus ikx e to the plus ikx, sorry, ikx dx, or this is equal to f of k 1 upon root 2 pi integral 0 to infinity f of x e to the ikx dx plus changing the variable from x to minus x in the second integral. We get integral 0 to infinity f of minus x e to the minus ikx dx. Okay, but because f of minus x is equal to f of right, f of k is equal to 1 upon square root of 2 pi integral 0 to infinity f of x e to the ikx dx plus integral 0 to infinity f of x the minus ikx dx. So as you will see the following, that is 1 upon integral 0 to f of x e to the ik dx equal to 1 half of f of k, right? Because it has to be minus infinity to infinity f of x e to the ikx dx is capital F of k. But and because f of x is an even function, I can write it as twice integral 0 to infinity f of x e to the ikx dx multiplied by 1 by root 2 pi, or I can write down that 1 upon root 2 pi f of x e to the minus ik e to the ikx dx is equal to 1 half of f of k. So this gives me f of k is equal to 1 of f k plus minus k by 2, since f of minus k complex function, what we have is equal to 1 upon 2 real f of. That means because the right hand side is real because of f of minus k is equal to f of k. So f of k is always real. So whenever you have an even function, the Fourier transform is real. So you similarly have things like Fourier transform of an odd function. is pure imaginary. You remember that we showed for Fourier series that a even function can be expanded in terms of cosine x and an odd function can be expanded in terms of sine x. Okay, so similarly here, the same thing, because the real and coefficients of sine x are imaginary. That is the reason why this happens. So you can also do the basic definition of what is Fourier of this and for finite t, and then the same problem. Okay, I presume there are some more. Okay, so that's what I'm saying. Proof of proof that minus infinity f of t d of minus t is equal to integral. Let me f of x g of x dx. I have just cancelled 1 upon root 5. Okay, so it doesn't matter. This is dk. Okay, now let us see left hand side is equal to 1 upon integral minus f of a integral minus infinity of 1 upon root 2 pi g of x. Sorry, 1 second. Let me remove this. What is 1 upon root 2 pi? The definition of the Fourier transform. Okay, so it's just f of k. So g minus k is 1 upon root 2 pi. We'll take it outside. Okay, g of x e to the minus ikx d. This is d of k. Okay, times dk. G of k is dx. Because you have to get a function of k, so that's the reason why you have to integrate over x. Okay, f of k is times d of k. Okay, is equal to 1 upon integral minus infinity to infinity gx. Okay, I'm going to change the order of the integration. Integral minus infinity to infinity. I'll take f of k e to the minus ikx dk times dx. Okay, I've just interchanged the order. And what is 1 upon 2 pi? Integral minus infinity f of a e to the minus ikx dk equal to, this is nothing but the inverse transform of f of k. So I must. So what I have, therefore, integral minus infinity f of k g of minus k dk is equal to integral minus f of x dx dx. Okay, so I have proved one, that is the Fourier transform of the product of functions is equal to the integral of the Fourier transform of a product of two functions f of k and g of minus k is equal to the integral of the product of the two functions in real space. So this is how the space link. Suppose so this is one of the it's called Parseval's first theorem, probably. I don't know which is first and which is second. But A is one of Parseval. Supposing G of x, then what happens is integral f of k f of minus k dk is equal to integral minus infinity to infinity g of x the whole square and x of x. So I have f of x the whole square dx or f of minus k is equal to f star k. Okay, therefore what we have, therefore integral minus infinity to infinity modulus x k squared is equal to integral minus k is equal to integral minus infinity to infinity square of f of x dx. Okay, so usually these quantities in k corresponds to omega or c, because 2 pi by k is equal to 2 pi by lambda. So that actually corresponds to 2 pi lambda bar, which is actually multiplied by c will give you the and x corresponds to this is what happens usually, because and integral of the intensity of scattering is the same in real and so this is called the power spectrum. Usually, you or in any physical problem, you call them power. So the power spectrum is the same whether you have it in k space or in omega t space, or if you have it in k space or x space. Okay, so this is one of the very important properties of Fourier transforms, and this one actually corresponds to one of the theorems. I think this is called Parseval's second theorem also. And from this you get but we will not go into that. So next, what I'm going to do is I'm going to discuss what's called so one of the things there are okay. These can be systematic. So when they tell you have frequency new, it is always for that particular frequency because it's not a sharp peak. We can never get a sharp peak. The grading through which has finite bits. If the width of the grading is finite, then according to that, the frequency of the wavelength. Okay, so this is the reason why you will have a systematic error because arising because of similarly, we can also have errors coming in from PES. Here, what we are doing is measured. Actually, you have analyzer. So, which allow electrons of definite speed to go through the hemisphere. So, what's that? Actually, let me just so the hemispherical and electrons. Then you have magnetic field. The electrons, okay, and only those electrons which have the same radius of as the analyzer. They pass, okay, and that means that uh, so these electrons have a specific velocity for a given. You remember the cyclotron, in which electrons are accelerated. So they are also go around the cycles because you are applying going back to the plane of the paper or the screen, and then the electrons go around some rule, and they go around, they will have a particular path. It is they will only go through. Okay. So usually this is this and the reason why it will have an error is because entry and exit. Okay, which means even electrons velocity, but it still can go through without getting discharged. This this thing, the sides of the hemisphere. So it should not. So usually because of this finitely split for entry and exit. And of course, if you are doing for what happens is the molecules are moving around the space, then we have an upper shift of the frequency. The line by the molecules have a frequency depending on the relative velocity of the molecule So if it is moving away from the source, then the frequency will shift downwards towards the source, then the frequency will become higher. And so the energy itself of the light beam that is actually hitting the molecule is going to be altered. Okay, so this is one of the things that will happen in this. So this also gives rise to spreading. So can be corrected. So these are because the Doppler shift depends on the speed of the molecules. Speed of the molecules, you know, the gas phase, and from the temperature, you know roughly what the shift in the frequencies will be, and so what will be the kind of function that you. So, this is not fusion. A convolution of the function. Okay. If a frequency position, okay, with intensity. Okay. So what is a signal which is okay. So the signal is what so this is some f of x which corresponds to f of or use So let me call this v1 and u1 and this function f of u1. Okay, and if the input intensity is going to be spread out over this two values, and at this u2, the intensity of the input is okay, and here again the signal is going to be present this way. Okay, and this signal function is the same, except it is shifted and it is lower in intensity. The signal f of this function actually, so this is actually u2 minus. Okay, so let me. So u2 minus u0. Then what happens is, let me take the intensity to be. So this is at I1, and this is going to be nu1 minus nu0. The first function is centered around nu0, so that way, okay, f of nu0, and to say all the other functions are centered around nu2 and so forth. Okay, I suppose this is clear. So what happens? The signal that come over I0 f of u0 plus I1, since it's only finite, let me write it separately. I1 f of nu1 minus nu0 plus I2 f of nu2 minus nu0. Okay, so this is what we have a frequency, the input frequency is at two values, nu0, nu1, and nu2, and I'm taking f of nu0 to be centered around nu0, and the others are all nu1 minus nu0. So you see that the nu1 minus nu0 is actually overlapping, and this one is overlapping here. Okay, so the overlap is always to the left side. That is the reason why I have taken it as nu2 minus nu0. Otherwise, what will happen? If you are shifting the functions, it is actually the right. The function is by say xi, then the function is f of xi. Okay, but here because you are taking the overlap to the left, it's going to be xi minus. So what this would mean is if the input frequency input function is continuous, the above summation goes over to an integration. And integration. Okay, so that will be signal will be equal to my output at a frequency which is fixed, let's say which is at nu naught. Okay, so you'll have to add up all of so that integral minus infinity I of nu f of nu minus nu naught d nu. Okay. So because I0 is I of nu. Okay. So this is intensity at u0. This is intensity at u1. This is intensity at u2, and so on and so forth. So you are actually summing over all these intensities. Okay. That corresponding to the signal corresponding to input frequency not u1, u2. So that is why that becomes a function I of nu, and the output is going to be f of nu minus nu naught, because the function is defined at nu naught and by progressively nu1, nu2, etc. So this is called convolution of the function I of nu, f of nu. Okay. So this is, so what it gives me is that the signal, let me I at nu naught is actually equal to the intensity of the input frequency. So this is input at frequency nu multiplied by the output at frequency nu, but the output function is defined at nu naught, so it has to be displaced by nu naught. And since you are taking the overlap to the left of the function nu, so it has to be nu minus nu naught. Cut. What it is? So it has to be not. Let me see why. Okay, I'll tell you why. Yeah. Nu naught minus nu. So this will be nu. I'll explain to you why it should be so. Just one second. So this is actually naught minus nu1. The reason is because I'm integrating over f of nu, right? So because I'm integrating over it, what I have done is I've shifted the origin of f of u to the right, and but overlapping that shifted function to the right to the left, and when you overlap to the left, it has to be nu naught minus nu, because when nu nu1 is greater than this thing, nu naught, then nu naught minus nu1 is negative. So which means that the function overlap. Okay. So I suppose to think about it and it will become clear. Okay. So what happens if I give you fx dx, then the convolution p or f is equal to integral minus f of tau minus v. Okay. So this is going to give me, this is the definition of convolution. This is what you get. So the convolution may involve, in this case, it has involved one or two functions involved. Is there, which is actually spreading out the signal. Okay. Now, so and you are integrating over x of f of x tau minus x dx. Okay. Now let us see why is this important, the concept, the context of this. Okay. It's quite easy to see something here, that is, if the observed signal is Fourier transform, what we get is a 1 upon root 2 pi integral minus h tau e to the minus I k tau d tau is equal to h of k. So my signal h of tau I know for every value of tau. For every value of tau, so I have to integrate it for every. Once I get h of now, let me put what I am doing here. Integral minus f of x d of tau minus x dx, okay, into e to the power minus I k tau d tau, because all I have done is use the tau minus x dx. Okay, so once I have done this, then I can, do the following, that is 1 of integral minus infinity f of x g tau minus x e to the minus I k tau minus dx, because you see that this is basically only a function of x, what I have here, tau is a constant here, then multiplied by e to the minus e to the I k x e to the I k tau e to the minus I k tau. Just 1 second, let me. So what I have got is, I'm writing this slightly differently. Okay, let me take out f of x outside. F of x, and I have integral minus infinity g tau minus x e to the minus I k tau minus x, and then this one is d tau into e to the minus I k x dx. I mean, just let me get it right. So e to the minus I k t minus x into e to the minus I k x. So I'll have e to the plus I k x and e to the minus I k x cancel. So this is correct what I have written. So what is this? Is equal to integral minus infinity 1 upon root 2 pi f of x into integral minus infinity g tau minus x to the minus ik tau minus x tau times, square root of 2 pi times into e to the minus ikx dx. So this can be written as g of k into integral minus infinity f of x e to the minus ikx dx to root 2 pi times dk f of k. Okay, I don't know. So for this, I should have taken, probably it will cancel somewhere if I were to do it. Okay, but basically that is h of k is equal to g of k f of k. That means if we have convolution of two functions f and g, f and g, then Fourier transform of the convolute is a product of the Fourier transform of independent independently functions. One second. One second. There's a phone call. I'll just. Hello? I'm not interested. Thank you. Okay. Telling my pen. So the same protocol is this. Get the h of x, Fourier transform it, and get h of k. We know the systematic error. F of x. We can independently Fourier transform because you don't require any measurement. Just Fourier transform. They're spreading the function that actually to get f of k, the Fourier transform of the signal g of x, which is capital G of k, is then given by G of k divided by f of k. So inverse transform G of k to get the signal corrected for the error spreading function. So with this you get the inverse transform of G from G of K, you can get G of X, so you can get eliminate the error, and this is done. So they, you know, data that you get from you have to actually Fourier transform for various functions which are actually scattering or spreading out the this thing, the signal beam. So this is done extensively in radio astronomy. It's also so in this sense, Fourier transforms are extremely important. And of course, I'll also tell you something else. Okay, so one of the places where in spectroscopy, you see particularly light has rather low intensity. Usually you use a klystron tube or something. So that is going to emit light mostly in the radiation, and this infrared radiation as a source in IR spectrum. So this is something that you must have actually learned when you studied spectroscopy. So if we mono the IR source, the intensity drops further because the black body radiation is going to tell you what the total intensity that is total energy that's emitted by the body which has been heated, say in this case to place to red hot temperature. And this is the total intensity, but if you monochromatize it, then the intensity at different wavelengths or different frequencies is going to be much smaller. And so if the intensities are small, then it's difficult to measure peak signal. So this has problems in obtaining sensitivity. Yeah. So you really cannot because it's like this. In 10 rupees, 50 rupees, then you want then you see that the number, the total amount is so that way just this is the number comes down for every frequency or every wavelength, the intensity is one of the problems. So the way is to avoid monochromatic. So what you do is the source Then you have with two parts. And then the middle is beam back. This is the other mirror. So when then what happens is you have an interference. Okay, and the interference pattern is actually contains all wavelengths of the beam that you have actually sent in itself in monochromatic. And now this one is going to the sample, and from there to the okay. So now you do this experiment with and without for different positions of the beam. So what you are going to get as a signal now is a difference in intensity with the sample and without the sample. Is also a polychromatic. So because the signal of this and get the signal you get is intensity as a function of time. Where time is the time it is position of the mirror. Now, if we transform the signal, we get intensity of intensity wavelength. So now with and without the sample, you know what the intensity is. So you know the difference is going to tell you. So this is what the Fourier transform usually does. Okay, and of course you also have Fourier transforms in NMR. Also Fourier transform is employed. Here what you do is that decay in induced band. Okay, if there is Fourier transform, to get the NMR. So this thing the magnetization decay that you are going to study in NMR is going to be very fast, and so you can signal averaging or many that you know magnetization decays. Accuracy of the experiment improves because it also uses this Fourier transform spectroscopy. Now the point is how to because the data the spectrum is continuous. So what we will do? So the spectrum. So this is time t. Okay. So we okay. So we exactly. Usually you discretize to n points. So n points with equal interval. So you have because I started with 0, it's going to be n points is going to be capital N minus 1. Interval is delta. Okay. So we have Tn n upon capital N. Okay. So the signal at the time of this by n times delta one interval. Okay. Now then, usually there is a very good reason. Use n is equal to where because there is a technique called the fast Fourier transform technique, which is made popular by Poulet and Tuque, but it was actually used first by Gauss in 1805 or something like that, you know. And so it is not something that is recent, but it was formalized by Poulet and Tuque and Lanchos. Okay, it was the one who put it on a in a form which is very easily understood. Okay, so we'll talk a little later, but right now let me tell you how you put your transform and how. So you have the R is an integer. So this is how 3 pi A is 1 upon usually you can read like same f of x e to the minus dx. So this I can write as upon root 2 into sigma over n equal to 0 to f of xn. Okay. Sorry, this is x. Xn is equal to n by n times lambda times e to the minus a. Okay. Xn here is n by capital N delta times dx is delta. Okay, because so this is a way of writing my using this thing, the usual Riemann integration formula and writing it as a discrete sum. So this will give me delta upon into sigma over n is equal to 0 to fn, because f of xn I call it fn e to the minus a n by capital N delta. I've taken out the common factor delta. Yeah. Okay. Now you see you have data. If you have data only at discrete points, you cannot get the function, the Fourier transform at all the continuous things. So k has to be different. So we say that k is equal to 2 pi by m, 2 pi by n, 2 pi by delta. Okay, so delta. I can write it as write it as 2 pi times some m divided by delta. Okay, so this is k. Okay, so if I did this, then my Fourier transform will be f am is equal to capital F. This is equal to delta upon square root of 2 pi sigma over n is equal to 0 to n minus 1 fn e to the minus I 2 pi mn by capital N, and delta cancel because you have a delta there and a delta here, and you have that. So in other words, what I have is I have discretized and I get delta upon root 2 pi because so this n is equal to 0 to n minus fn e to the minus I 2 pi mn by capital. Now what I'm going to do is define a quantity. Define W is equal to e to the minus 2 pi I by. Okay, so it is such that when you have e to the minus I 2 pi mn divided by n is equal to W to the power. Okay, so what you have got from here is the power. Fn equal to sigma over n equal to W to the power n Fn. Okay, so this is almost W to the power mn n. So I have something that goes as W squared W to the power x W to the power 4 and so on. So you can just write it down by writing it. So mn is so when m is equal to so all this will be 1 because m into n is 0 is 0. Okay. I across j column across. Then the next one will be then this will again be 1. W to the power n minus 1, and the next one will be when n is equal to 2 and so on, and here I'll get. Okay, so this is the matrix W. One second, let me get it. Okay, so the entire thing is like a matrix multiplication. Okay, so Fourier transform is nothing but matrix multiplying into a vector. So what I have is F1, F2, etc. For the F0, F1 to Fn minus 1 is equal to W to the power 0, W to the power 0, etc. W to the power 0. And then this is W to the power 0, W to the power 1, etc. W to the power n minus 1. And then I have one is again W0, W squared, W to the power 2 times n minus 1, and so on and so forth, which is multiplying into F1, F2, F3, Fn. So, how many then how many times I have to multiply? See, if I want to multiply get F0, I have n multiplications and n addition. Usually, additions don't cost extra time. Additions come at simple overheads, simple, it's taken care of because when it's actually when parallel processing is taking place, then at that time the addition simultaneously. So additions comes at no cost. So to get F0, I have to have n multiplications. So to get the full vector F, to get the full vector F, I require n because for every component it is n. So then we have to perform n squared operation. Okay, but there's a way of actually rearranging my calculations in such a way that we can such that the Fourier transform can be done in n log to the base 2. Okay, so n log to the base 2. So I said earlier that you always prefer to have n as equal to 2 to the power r. So if n is equal to, then number of operations is n log 2 to the power r. 2 is equal to n. Okay, so suppose we have a million data points. Okay, what is a million in powers of 10 or powers of in powers of 2, 8 to the power 6 is roughly equal to 2 to the power 30. Right? No, sorry, this million is 2 to the power 20. Right? Because 1,000. So that is what you mean by kilobyte, right? Kilobyte is 1,004 bytes or 10. And a megabyte is 1,000 of those. So this 2 to the power 10 into 2 to the power 10 is 2 to the power 20. Okay, now let's uses n squared operation or 10 to the power 6 or 6 is equal to 10 to the power 12. 1 giga operations. Okay, 10 to the power 12 operations. So if you do it, we'll take 10 to the power 6 into log the base 2 equal to 10 to the power 6 log to the base is equal to 30 into 10 to the power 7. I mean 10 to the power 6 or 3 into 10 to the power 7. Okay, so this is about 30,000 times cost. Okay, so for example, if you are doing an NMR spectrum, okay, and if you are doing a fast Fourier transform, then you can average over 3 more than if you are doing a slow Fourier transform. Much longer, almost 30,000 times longer. So if the then the slow Fourier transform will take 500 hours, right? 500 minutes, not 500. So it will take 500 minutes because 300 seconds is 5 minutes. So it's 500 minutes it will take if you are to do an ordinary Fourier transform. So you see the speed of calculation. Now let us say how we can in order to do that, let me write down how the so suppose I'm looking at the Fourier transform. Function f of x, which is split into f j. J is equal to 0. And I want to find out what is f k, okay, and k is equal to 0 and 1. Exactly the same way. So what is equal to sigma over j is equal to 0. It's a 2 pi j k minus, here I have taken transformation to be e to the power plus kx, but not really this times f of k. So what I did, yeah, I take it. So we can break up into summation for all k given. So if I did this, what happens? This I can write as sigma of k, I mean, is equal to sigma of j So sigma over T equal to 0 to n is actually divisible by 2 because it's 2 by h 2j. Two j by n plus sigma over j is equal to 0 to e to the power 2 pi I for this multiplied by n. Okay, and this is 2 pi I k times 2j plus 1. It has to be 2j plus 1 because odd means it will start with j is equal to 1. Okay, 2j plus 1 divided by n times f of 2j plus 1. Okay, so now you see and write e to the power by k 2j on n f of 2j plus w to the power k. Remember w was 2 pi I by n. E to the power 2 pi I by n was w. So w to the power k will take sigma over j is equal to 0 minus 1 e to the 2 pi 2j by n times f of 2j plus 1. Okay, so two Fourier transforms. You have broken up the first Fourier transform or the entire set of data n into two separate sums. One involving Fourier transforms of only the even data points, and the other involving Fourier transforms of only odd data points. So this is Fourier transform of odd data points. And this is Fourier transform of even data. So one is so I can call this one as f of a is equal to f of k is equal to fk e1, which is the one of e1 set of the other one is k f of k of odd set of. Okay, now I can take fk of e. So this is going from n by 2. Okay, and what I can do is I will change the summation as so. How will I change it? I'll change it by sigma 1 is n by 4. Okay, because earlier it was n by 2. Now I'm going to have n by 4 points, and 2 pi k j by okay times f of 4j plus sigma over j is equal to 1 e to the power 2 by I k times k plus 1 divided by n divided by n, because it's always having even ones. Okay, f of 4j plus 2. Okay, so it's as if you had 2j plus 1 into 2 and 2j into 2. Okay, so now all those divisible by 4. Okay, I collect them together, and all those that are divisible by 2, I collect them together within the even one. In the odd part, nothing is divisible by 2 or 4, because it's all f1, f3, f5, f7. Whereas in the even part, everything is divisible by 2. So I'll take those which are divisible by 4 and call them f4j, and I have Fourier summation j equal to 0 to 4 by n by 4 minus 1, and the other one is j equal to 0 to involving f of 4j, that is a functions evaluated at 4j points, k equal to 4j, and the others are those which are evaluated at 4j plus 2. Okay, so what will happen? So this I can write fke is equal to sigma over j is equal to 0 to minus 1. Need the 2 pi I k times 4j divided by n of 4j plus e to the power 2 pi I 2k by n sigma over j is equal to 0 to n by 4 minus 1 e to the power 2 pi I k times 4j by n f of 4j plus 2. Okay, so this will give me fk even. Okay, because even means divisible by 4. Okay, it is even once, so you divide again it's even by 4. Okay, and the other one is actually plus w to the power 2k, because e to the power 2 pi by I by n is equal to w, so it is w for 2k. This is k even odd. Okay, so I can write down my Fourier as equal to fk even plus w to the power 2k fk even odd plus the same will go there k fk even odd, then plus 3k fk odd. Okay, so e means even and o means odd. So the first time you have taken even, that will become fke. Again, take from there. That is those that are 4 the points. Then it will become fk even, and so forth. So what I'll do is I'll continue from here. Now this whole computation that are required, and this is not the launches. Okay, until then we can break. So we'll meet again on Wednesday. Just a minute. Okay, so stop sharing. and we can move on. Okay, thank you.
Thank you, sir.
Okay, bye.
Bye, sir.